Hello everyone, this is Dr. Webb. So over the last couple of videos we've been working with double integrals. Now it's time to add one more dimension in and talk about triple integrals. The theory behind this is not that much different than double integrals. You know, the big jump is moving from a single integral to a double integral. Going from double integrals to triple integrals, it's really the same idea. But let's just, do a quick review of what we saw with double integrals. So double integral, we're integrating some function of two variables over some region, and we use dA as representing sort of little bits of area. And so remember, the idea is R is some region on the xy plane usually. And what dA is coming from is we're measuring this over little bits of area. And so you can think about little bits cut out by delta x and delta y, put these together, they become delta A by multiplying delta x and delta y together. And then we take our limits, and dA is equal to dx dy, or dy dx in some order in that way. Okay, so what happens when we add one more dimension? So in 2 dimensions we had flat regions. In 3 dimensions, now we're going to be integrating over solids. So moving up one more dimension, now we're going to have 3 integrals where we're going to be integrating over some solid. Perhaps we're integrating some function that has 3 variables in it. And now, rather than little bits of area, we're going to have little bits of volume. So we're going to use dV as our measure. And so if you think about this, we have some solid now in 3 dimensions. And we're imagining breaking this up, instead of into little rectangles, now we're breaking it up into little boxes. Okay, where the boxes are delta x, delta y wide, delta z high, and so our little bit of volume is the product of delta x, delta y, delta z, and then when we go through and take our Riemann sum and take the limits, dV is dx, dy, dz, or some other order. You know, for 3 of these, there's actually 6 different orders you can put them in. So I'm not going to write them all out, but this is what's going on. And the same idea with each integral, you're taking care of one variable at a time, right? So let's just jump in and start doing some examples. Okay. So first one, we're evaluating, we're integrating this function x squared y minus 2z over a box. And so the box, you can see that there's no, in these bounds, x is going from 3 to 5, y is going from 1 to 2, z is going from -1 to 3. And so there's no dependency between the other variables in these bounds. So this is just like integrating over a rectangle for a double integral. And so in this case, it doesn't really matter what order we do this in. So if we're doing x squared minus y, x squared y minus 2z, let's say it doesn't really matter, so let's do y first, and then we can do z, and then we can do x. Now we need to make sure that we have our bounds lining up. So inner ones are going with y, next ones are z, so -1 to 3 connects with z, and then our last bound going from 3 to 5, that's connected to x. Okay, and so this is the integral that we're doing. And how do you do a triple integral? Well, same as any other integral, any other multiple integral, you just do it one at a time, working from the inside out. Right, so first, after I erase all of this, okay, so we're going to do the inside integral first. We're integrating in terms of y first. So x squared times y, integrating in terms of y, is going to give me x squared y over 2 minus 2 zy, and our y's are going from 1 to 2, and so plug that in, should be y squared. So 2 squared minus 1 squared, 4 minus 1 is 3, so this gives me 3x squared over 2 minus 2 minus 1 is 1, so minus 2z. So that's what we get from the inside integral. We go and we plug that in to the next integral. And so now we have 3 to 5 minus 1 to 3, 3x squared over 2 minus 2z. Notice that we have completely gotten rid of the y's. So now we're just integrating in terms of z, dz, and dx. And this is like any other double integral we've seen, two variables. So now we're integrating dz. So 3x squared over 2, that's going to become 3x squared z over 2 minus z squared. And then we're evaluating this from z, goes from minus 1 to 3. And so, let's see, 3 minus minus 1 is going to be 4. And so 4 over 2 is 2, so I have 6x squared minus, so 3 squared minus minus 1 squared, so 9 minus 1 is 8. And so we're left with, from the second integral, x squared minus 8, and we plug that finally into the last integral. And so we've got 3 to 5 of 6x squared minus 8. Now we're integrating in terms of dx. And so this is going to be 2x cubed minus 8x, as x goes from 3 to 5. 5 cubed is 125 minus 27, so that would be 98, times 2 is 196, minus 8 times 5 minus 3 is 2, so minus 16, and so I think this ends up being 180. Okay. And so it's not really any harder than doing double integrals, it's just 50% longer because you've got one more variable to integrate against. Okay. So boxes are easy. It gets a little bit harder, a fair amount harder when you're actually doing this over solids that aren't boxes. The ideas are exactly the same as how we broke up regions for double integrals, deciding whether or not we wanted to integrate over horizontal lines first or vertical lines first. It's just now we have three choices. And this also is where it gets to be more difficult to see exactly what's the solid that you're integrating over. You know, we've been trained to think about things in 2 dimensions quite a bit, and you've gotten a fair amount of practice in drawing and looking at shapes that are created in 2 dimensions, not as much in 3 dimensions. And so this is where this really at times can really test your 3 dimensional visualization skills. So let's try and do a rough drawing of this region. So we're integrating x times y over a solid where the top is the plane z equals 2x plus y plus 6, and the bottom is z equals minus x minus y plus 4. And over the triangle on the xy plane bounded by the x-axis, the y-axis, and the line x plus y equals 1. Okay, so first let's get an idea about these planes. So I'm drawing out a quick axis. So z equals 2x plus y plus 6. So let's think about what happens on the xz plane for this. So that's setting y equal to 0. And so this is going to look like z equals 2x plus 6. And so starting off at 6, and then it's going up kind of slope 2 on the xy plane. And then let's make that a little bit steeper. So going up slope 2, up like that. And then on the YZ plane, so that's when we set x equal to 0, this is going to be z equals y plus 6. And so that's going to be slope 1 on the YZ plane. So you can kind of see we have this plane coming out in the first octant like that. On the other hand, z equals minus x minus y plus 4. So that's starting at 4 on the z-axis. And let's do the same idea. If we do z equals minus x plus 4 for the zx plane, xz plane, so this is going to be going down slope 1. And on the yz plane, it's z equals minus y plus 4. So this is going down. And so we're getting this, that plane going down like this. And then it said this is all happening over the region between the x-axis, the y-axis, and x plus y equals 1. So x plus y equals 1 is going to cut this out here. And so you can kind of imagine that we have this sloping down here. So it looks kind of like a triangular prism, but the top and bottom are not cut straight. So if I zoomed in on that, it would look roughly like that. Where, let's see if I can dot some lines here. These are sort of on the inside. Okay, so that's roughly what the solid looks like. Okay, and so we kind of have to pick one direction to integrate first. And this one is very much set up to integrate z first. And sort of the idea is that if you take some point on the xy plane, we're going to integrate over the z values between it. So we're going to integrate over a straight line going up. Okay, and so that's our bottom plane, that's our top plane, and so our bounds for z are going to go from the bottom plane, minus x minus y plus 4, to 2x plus y plus 6. Okay. And so for any z value over that region, these are the z values that we're going to integrate over. Now let's focus in on this region on the xy plane. And so I'm going to draw it, rather than in 3D, draw it in 2D on the xy plane. And so now this is just like doing a region that we did with double integrals. And so this region, the line is going to cut across like this, and it's the region bounded by these. And so we got to decide whether or not we want to do horizontal lines or vertical lines. It doesn't really matter. Let's do vertical lines. So at some x value in between 0 and 1, we're going to be integrating from y equals 0 up until, solving for y here, y equals 1 minus x. So our y values are going from 0 to the line 1 minus x, and then the x values here are going from 0 to 1. Okay. Yeah, and so these are going to be our bounds of integration. Okay. So one way that I really want to emphasize in thinking about this is we kind of took care of the z variable, and then what we had left was a double integral on the xy plane. And so we can just use what we know about double integrals on the xy plane to do this. Okay, so really, let's integrate this the z variable and see what we have. Okay, so let me see if I can add a slide here. Yeah. So let's clear this out. So let's copy out our bounds up here. So we're going to be going 0, x, 1, 0, y, 1 minus x, and then minus x minus y plus 4 less than or equal to z, less than or equal to 2x plus y plus 6. Okay. Let's leave that picture there. Okay. So really the way that I'm thinking about doing this integral is we're going to integrate in terms of y first. And so the function we're integrating is x, y. We're going to integrate that in terms of z. Okay. And then when we're done with that, we're going to be left with a double integral over this region R. And so after that, we have a double integral over R in terms of dA. So this dz times dA, that's dv. We're just pulling one out, and we're going to be left with dA after that. And so we can do this integral. And so it's xy integrating in terms of z. So there's no z's there, so we treat xy like a constant. And so we have x, y, z going between these two planes, minus x minus y plus 4, 2x plus y plus 6. Plug these in. This one I can't do in my head. So we're going to get xy times 2x plus y plus 6 minus x minus y plus 4. And so I think we end up with x times y times 2x plus x gives me 3x. Y plus y gives me 2y. 6 minus 4 gives me 2. And so this is 3x squared y plus 2y squared plus 2xy. 2xy squared plus 2xy. Okay? And so that's what we get from doing the innermost integral in terms of z. And so now we're going to plug this back in and do our double integral in terms of x and y that's left. And so important thing to note, at this point all the z's are gone. We have completely eliminated the variable z, and we are down to a 2-variable problem. So let's clear this out. By doing that integral, we have eliminated z, so let's take that integral out. And so now we are integrating 3x squared y plus 2x y squared plus 2xy over this triangular region, which we'd already broken up before. Okay, and so dA, we decided that we were going to do y first, and then z, y first and then x, and so our bounds for y, are 0 to 1 minus x, and then our bounds for x are going to be 0 to 1. And so now we're doing this, we're doing this inside integral now in terms of y. So, let's erase this all up. Now I think we can clear out this region. No, that's not what I want to do. Sorry about the mess. The eraser in this program does not always work well. Okay, so let's do it. So we're integrating 3x squared y plus 2xy squared plus 2xy in terms of y. So I get 3x squared y squared over 2 plus 2/3 xy cubed plus xy squared, where my y's are going from 0 to 1 minus x. The 0 is nice because that's going to clear everything out, so I'm just plugging 1 minus x in everywhere for y. And so I have 3x squared times 1 minus x squared over 2 plus 2/3. Oh, come on. Give me a little bit more space. Actually erase. There we go. Okay, plus 2/3 x 1 minus x cubed plus x times 1 minus x squared. The squared should be on the outside. Okay, so this is looking a little bit nasty, but it's just polynomials, so that's not too bad. So this is going to be 3/2 times x squared times 1 minus 2x plus x squared plus 2/3 times x times, I'm just going to do this cube quickly, 1 minus 3x plus 3x squared minus x cubed. You can double check me, but I am positive that's correct. And then the last one is going to be plus x minus 2x squared plus x cubed. Okay, so let's write this in how we want it to be in our integral. Now again, deep down, these are not actually evaluating these integrals. It's not difficult. The difficult thing is just, getting the will to do it. Okay, so all of these have x's in them. So I think so I get 2/3 x plus another x, so that would be 5/3 x. Okay, for my x squareds, I have a 3/2 x squared minus 2x squared coming here, minus another 2x squared. And so that would be so 3/2 x squared minus 4x squared would be minus 2.5, so that'd be minus 5/2 x squared. Okay, then for my x cubes, I have minus 3x cubed. Let's keep a little tally here. Minus 3x cubed plus 2x cubed plus another x cubed. The x cubes, it looks like they all cancel themselves out. And so that's going to be no x cubes. And then for x to the 4th, I have 3/2 x to the 4th coming from here, minus 2/3 x to the 4th, and that's all the x to the 4th, so 3/2 minus 2/3, so that's 9/6 minus 4/6 is 5/6. So let's double check this. So minus 3x cubed plus 2x cubed plus another x cubed. Yeah, the x cubes cancel off. Okay, I think this is right. Let's just go and assume that it is. Okay. So, down the last integral. So, integrating 5/3 x, so this is going to be 5/6 x squared minus 5, 6, x cubed minus 1/6 x to the 5th something here is not totally right because I'm going to be getting a negative answer, but oh well. Oh, this should be plus 5, 6. That's right. So that becomes plus 1, 6. Okay, now I'm happier. Okay. And so when I plug 1 in here, the 2, 5, 6 are going to cancel themselves off. And so at the end of the day, I'm left with just 1, 6. And that should be plugging in 1, not 4. Only took a little bit over 20 minutes to do. Okay, but that's what triple integration is. Okay, so we're going to do 2 more examples, but we're not actually going to set up the integrals. We're just we're not actually going to evaluate the integrals. We're just going to set them up, and so we're just going to set this up with some dummy 3-variable function inside of it. Okay, so in this case, the solid is just the area that's bounded by 2 surfaces. Okay, and so one of the things we have to do is, so in this one, these are both set up as z equals, and so the fact that they're both z equals, it's sort of suggesting that it makes sense to integrate z first, again. But one of the things that we then need to do is figure out what's the region that this is over. So it's saying that these are bounded by these 2, so these 2 surfaces must hit each other. Okay? So the big question now is, where do these surfaces intersect? Okay, so let's get a rough idea of the picture. Okay, so the first one, 8 minus x squared minus y squared, that's what's called a paraboloid. We've seen these before. And so if you think about what's happening both on the xz plane and the yz plane, we have, starting at 8, we have parabolas going down, like so. And then if we set z to be a constant, then you have a constant is equal to 8 minus x squared minus y squared. We can move the x squared plus y squared to the other side, and you're going to end up with circles in some sense. And so the cross sections here are going around like a circle. Z equals 4x, so this is just a plane slicing up like this. And so this is actually going to cut. So this plane is going across this way. This is going to be hard to see. Okay, so the plane is cutting out like this across. Okay, and it's the intersection between these two is going to produce some sort of region that this is happening over on the xy plane. Okay, from the picture, what we can see is that it looks like for the region bounded between these two, the paraboloid is on top and the plane is on the bottom. And so that gives us enough, we don't need to have a perfect picture of the region on the xy plane from here. From this picture, really all that we needed to know is, since we're integrating z first, what's our bottom function and what's our top function, right? And so for some xy point on the region, we're going to be starting on the plane, integrating up until we hit the paraboloid. Okay. So our z bounds are, we're starting from the plane, which is 4x, going up to the paraboloid, 8 minus x squared minus y squared. Okay, so now we need to figure out where these intersect, but we just really want to know what are the x and y points in the intersect. We don't really care about z anymore because we've taken care of z here, right? And so since both of these are z equals, we can just set the two equations equal to each other, have the z gone, and now we're left with just a equation just in terms of x and y, right? So the x and y coordinates where these surfaces intersect, well, that's where 8 minus x squared minus y squared equals 4x, right? So notice that this is just in terms of x and y now. Okay, so we can rearrange this, have this as 8 is equal to x squared plus 4x plus y squared. It's x squared plus 4x plus y squared. Okay. You know, my mathematical knowledge is telling me that this is going to be a circle, but it's not centered at 0, 0. It's centered off. And so to figure out where this is centered, I'm going to complete the square for x squared plus 4x. And so to complete the square there, I need to add a 4. And if I added the 4 to the right side, I need to also add a 4 to the left side. And so this is going to become 8 plus 4 is 12. Okay. And so then I have 12 is equal to x squared plus 4x plus 4 is x plus 2 squared plus y squared. And so this is a circle that's centered at minus 2, 0. Okay, and the radius of this is going to be square root of 12. Although that's not too important. What's important is that I have this broken up nicely between x and y, and so I can solve for one of these. In fact, I didn't even really need to get to this point. This really gives me everything that I want because I have a single y here. Right? And so that's the equation that's giving me my region on the xy plane. And it does happen to be a circle. And so on the xy plane, so this is a circle centered at minus 2, 0, has radius square root of 12, which is a little bit more than 3, less than 4, so it's roughly looking like this. Okay. Let's close this off. Okay. And so I'm going to solve for y, which means we're going to be integrating over vertical strips on here. And so I have y squared is equal to 8 minus x squared minus 4x. And so this is really important to use when I use the square root, that I am really breaking this up into two separate curves. That's going to be the positive side of the square root. That's going to be the negative side of the square root. And so when I'm integrating, I'm starting on the negative square root and going to the positive square root. So my y's are going from, let's give myself a little bit more space. So my y values are going from minus square root of 8 minus x squared minus 4x to positive 8 minus x squared minus 4x. And then last but not least, my x bounds, well, so it's centered at minus 2. The radius is square root of 12, and so it would be minus 2 minus square root of 12 for x to minus 2 plus square root of 12. Okay, so there's our bounds. Let's copy these up. So we're integrating in terms of x last. So let's put them on top. It's 2 minus square root of 12 minus 2 plus square root of 12. My y bounds are minus square root of 8 minus x squared minus 4x positive square root 8 minus x squared minus 4x. And then the z bounds, I'll have to fit them in over here. 4x less than z less than 8 minus x squared. Right, so, this only took a bit more than 10 minutes just to set this up. So let's clear stuff out here. Okay. Now we've got lots of nice space to write out our integral. Okay, so we're integrating f of x, y, z. First, we're integrating in terms of z, and so the z bounds 4x, 8 minus x squared minus y squared. Then we're integrating in terms of y, and the y bounds go from minus square root 8 minus x squared minus 4x to 8 minus x squared minus 4x. And then last but not least, going from minus 2 minus square root of 12 to minus 2 plus square root of 12 for dx. Whew! Okay, so we're done. This is it. So one thing to note in here is that, so first we're integrating in terms of z, and what do we have in the bounds for z? Well, we're allowed to have functions that use both x and y, right? But after we do this first inside integral, all the z's are going to be gone, and we're going to be left with things just in terms of x and y. Okay. And then, now we're doing the second integral, the blue integral, for dy. Well, for dy, we're allowed in the bounds to have functions that involve just x. X is the only variable that's allowed to appear there. And so then when we have this integral that has x's and y's in it, we integrate in terms of y, plug in the bounds. After that, we're going to have an integral that just involves x, right? And so then our last integral, we're integrating in terms of x, and our bounds are constants. And so when we integrate this out, we're going to end up with an actual number. Okay. And so this is the way that has to happen in these bounds. And the outermost bound has to just be constants for the bounds. The next one in can have just the variable that's going to be integrated last. So in these bounds for y, these can have x's, and in the bounds, the innermost bounds, these can have x's and y's. Right? And it's, you just think with each integral, you're eliminating one variable at a time. So the black one eliminates all the z's. The blue one is going to eliminate all of the y's. And then last but not least, the red integral is going to eliminate all of the x's. Whew. Okay, one more example. I think this is going to be the longest video for this course by far, and also I think it has the least number of slides. So, one last one. In this case, so we're integrating, just setting up the bounds again. This one I may do a little bit faster. The one thing to note is we're again doing it between these two surfaces, but what these two surfaces, the equations for them have in common are the y's. Right? And so since both of these have y's, and they're actually both easy to solve for y, this is suggesting we're going to integrate over y first. Okay, so let's get a quick rough idea of what this is looking like. Okay, so the first function is y minus z squared equals 1. So we can think about that as being y equals z squared plus 1. Okay, and so if this on the yz plane, this is going to cut out a parabola opening up along the y-axis. And so we have this parabola on the yz plane, and then this is just going to go out. Right, it's just coming straight out along the x-axis. So it's just the parabola coming out. On the other hand, we have y is equal to minus 3x squared equals 6. And so if we go out 6, this on the xy plane is going to be a parabola going down in the x direction. And so this parabola is going to be going out like this. And so you can kind of think about these as these are like two parabolic sheets turned at a 90-degree angle to one another and coming together. Okay? And so just thinking about this, if you close your eyes and even try and think about this for 30 minutes, it's still going to be pretty rough to figure out exactly what this intersection is going to look like. Luckily, we're going to just trust the algebra on this rather than, trusting our poor three-dimensional minds. But if we're integrating over y first, we're thinking about taking some point on the xz plane and going through all the y values from that. And so as we're going out from the yz plane, you can see we're going to hit the blue parabola first, and then we'll be integrating until we hit the red parabola. Okay, and so what that's saying is that the y minus z squared equals 1, that's going to be our inner surface, and the 3x squared plus y equals 6, that's going to be our outer surface in terms of y. So our bounds for y is going to be z squared plus 1 going up to minus 3x squared plus 6. Okay, so since we're integrating in terms of y first, we're allowed to have x's and z's in our bounds. Okay, now we have to figure out what this region of the intersection is happening over on the xz plane. I'm going to use the same trick as before, except now we're going to solve both of these for y, which we've already done, set them equal to each other. Okay, so now we've got z squared plus 1 is equal to minus 3x squared plus 6. So let's move these all to the same side. So we have 3x squared plus z squared equals 5. And so this is going to be an ellipse. We're going to have 3/5 x squared plus z squared equals over 5 equals 1. Okay. So on the xz plane, let's see, can I erase just you? Yes. Okay. So if we're looking at this on the xz plane, so let's call this the x-axis, this is the z-axis. So this is an ellipse. I believe this is going to be longer in the z direction than the x direction, although it's not that important. Looks roughly like that. I'm going to say that we should integrate in terms of z next. And so in this picture, we'd be integrating over vertical lines. And same as before, we're going from the bottom half of the ellipse to the top half of the ellipse. And so we need to be careful with the signs when we take the square roots, because the negative part of the square root is going to be our bottom bound, and the positive side of the square root is going to be our top bound. Okay, so taking this, solving for z, z squared is equal to 5 minus 3x squared. So z is plus minus 5 minus 3x squared. And so our z bounds are going from minus 5 minus 3x squared. And then our upper bound is 5 minus 3x squared. Okay. And then the x values are coming from when z is equal to 0. Right there. And so when we set z, go back to this equation and set z equal to 0, our x bounds are going to be coming from 3x squared is equal to 5. And so x is plus or minus square root of 5/3 is where these are. And so x is going from minus square root of 5/3 to positive square root of 5/3. Okay. And so these are our bounds. Let's write the integral. We got to clear some space out again. Oh, nice. Let me do that. Okay. So we have our bounds down there. Let's write this up. Okay, so we're integrating our dummy function. So first we're integrating in terms of y, and the bounds for y can have x's and z's in them. Okay, then we're integrating in terms of z. Minus 5 minus 3x squared, square root of 5 minus 3x squared, and then lastly integrating in terms of x. And the bounds for our last one are just constants. Minus square root of 5 over 3. Square root of 5 over 3. That square root covers the 3. Both of those. Okay, and so just to double check, our inside integrals, we're going to be taking care of the y's. Our bounds have x's and z's in them. That's okay. Okay, our next integral, so the y's are gone. Now we've just got x's and z's. So then we're integrating over the z's, and our bounds can have x's in them. That's okay. And then last but not least, we're only going to have x's left, and our bounds for integration are just constants. And so that's going to take care of the x's. And we're going to be left with a number, and we're in good shape. Okay, so this is the idea. This is the process. As you can tell, this is not this. It took us, even this one, it took us about 10 minutes just to set up the integral. This is not a quick process. You have to take your time, be patient with yourself, and just do it bit by bit, breaking it down. Okay? Don't get too, don't get too hung up if you're not seeing the whole picture at once. You don't need to see the whole picture at once. You just need to have a good enough idea of how you take care of the next variable, right? Deep down in this one, we just needed to know at the beginning, we decided we were going to integrate in terms of y. So what is the function on the left and what is the function on the right to get those bounds right? Okay, then we eliminated the y's. Now we're left with just a two-dimensional problem in terms of x's and z's, and then we work to take out the z's, right? So just do it step by step, slowly. Don't try and force yourself to understand everything at once. Just understand what you're trying to do right now in terms of getting rid of one variable at a time. So that is all. Enough philosophizing from me. I will see you all soon.